Hi everybody, this is Mr. Nolan, and I want to talk to you about calculations for the river project. There's 6 of them, and we want to be able to figure out what are these calculations and what do they mean. An important note, a couple of important notes, is that it is absolutely essential that you can do at least some of these calculations for your project. You don't have to be able to do all of them, but you should at least be able to do a few of them with some precision. These indexes are useful measures of biotic factors. So if you're trying to figure out, well, how does A affect B? B is a biotic factor, and we want to be able to calculate some of these biotic factors based on the organisms we find out there. And it's also very useful to investigate how different environmental changes affect these factors. So these are going to be very important for our project. There's 6 of them. There's 6 indexes, and they are they sound kind of complicated. There's really not too much to them. We'll go through each one and we'll figure out what are they for. The first one that we'll learn about is the Autotrophy Heterotrophy Index. This is pretty simple. It just calculates how much algae is in the water. And we'll look at the equation in a second. But that's what you would do if you were trying to figure out, well, either how much algae is there, so I want to figure out how does algae affect other things, or maybe you want to figure out maybe like how the annual changes in the environment affect the amount of algae. To calculate this one, what you would do is you would take your numbers, and we'll learn how to take these numbers, where do we get these from later, and we have to set them up in a very particular sort of equation, this calculation. So I have to take the number of scrapers, this is that feeding group, right, scrapers, for 2015 there were 43, and then I have to divide that by the sum of the shredders, gatherers, and filterers. So remember, these are feeding groups. These are different kinds of eaters. They're not species, they're different feeding groups. And this index tells us how much algae is out there. If there's more scrapers, then there must be more algae. So I'm going to go ahead and write this up here, just so that we can try to figure out, well, what numbers would we use? Our scrapers are down there, shredders are here, gatherers, and then filterers. Okay, so I'm going to write that up here so you can see what that equation would actually look like. Okay, so here's what I did. I took my scrapers, those are in red here, and I put them right here. I did divided by the shredders. Here they are, the shredders are down here, and I put them there. My gatherers are right here, that's where I found them. And then my filterers here were right there. Okay, so and then my scrapers were right there. So that's where I found my numbers. And if I calculate that properly, what I end up with is 0.153. Most of these indexes are going to be between 0 and 1, right? So they're going to be greater than 0, but smaller than 1. So most of my indexes are going to be a decimal, some kind of a decimal. So what we're going to do here is try to analyze this. What is this supposed to mean? Well, it's a really small number. It's close to 0, 0.153. And what that means is that most of my food at this year, 2015, was not produced by algae. If it were produced by algae, this number would be a lot larger. It would be closer to 1. And so in this case, well, most of our food is really not produced by algae. So let's go ahead and look at some other indexes. They all work pretty much the same. They're pretty much plug and chug. Okay, so now that we know autotrophy, heterotrophy, let's look at FPOM, FPOM index. What this is this is an index that shows you how much of the food is in big chunks or big pieces. If you get a large number, it means most of the food is in things like grass clippings, leaves falling into the water, sticks and twigs, and other sort of chunks of big food. So to do that, all we have to do is take our shredders and divide them by our total gatherers, and that's because shredders eat FPOM and the gatherers eat FPOM. So let's look at what that equation, what that calculation would look like. Shredders divided by gatherers plus filterers. So there's my shredders, 27, there's my gatherers, 246, and there's my filterers, 8. So let's go ahead and set this up and look at what the solution is. Alright, so what I get here, I take my 27 shredders divided by my 241 gatherers plus my 8 filterers. And if I go ahead through with that calculation, I get 0.106. And I'm always going to round to the thousandths, by the way. Round to thousandths. This will maintain enough precision without going too crazy with the decimals. And so what this would mean is that again, it's quite low, so that means that my CPOM FPOM index is low, and I don't have a lot of CPOM. This is very close to 0. If it were closer to 1, it means that lots of my food would be CPOM. Coarse, particulate organic matter, as opposed to FPOM. So because our number is so low, all that means is that most of the food that we find is actually FPOM. Okay, that's what that means. Low number for this means that we have a lot of FPOM. So let's look at our other equations. FPOM in transit index. So what this means, we use this to determine how much of the FPOM is floating in the water. So we just talked about CPOM, FPOM, coarse particulate organic matter versus fine particulate organic matter. If we just wanted to look at the FPOM, we can figure out, well, is it floating in the water or is it stuck to the river bottom? So to do that calculation, we take we take our filterers, divide it by our gatherers. That's pretty easy. So all that we would have to do is just go ahead and take 8, divide it by 246. So 8 divided by 246. What we end up with is 0.033. Again, if we round to the nearest thousands. Okay? So this would also mean that our FPOM in transport, there's very little FPOM in transit. So most of the FPOM in this ecosystem is actually not floating around, it's sitting on the bottom of the stream. I got my 8 filterers from down here, I got my 246 gatherers from right there, and this gave me this number. So very, very little FPOM is actually floating. Most of it is sitting in the stream. Substrate stability index tells us how stable is the surface of the riverbed. So if the riverbed is not stable, then we're going to have a low number. If it's very stable, we'll have a high number, like closer to 1. Now you might guess from walking around out there, watching people walk around out there, that it's probably not a very high number, and you would be right. So to calculate this, what we would do is we would take scrapers and filterers, we would divide that by gatherers and shredders, which I've sort of abbreviated here for space. So scrapers and filterers both need something to cling on to. And so if there's a lot of them, that means that it's a very stable substrate. So there's going to be a lot of rocks and things that are not moving around very much. Gatherers and shredders don't need to cling on to anything. They can just kind of crawl or swim around. And so if there's mostly gatherers and shredders and we have a low number, that means that our substrate must not be very stable. So let's go ahead and set this up and figure out what our answer is. Alright, so when I set this up, it looks like I've got 43 plus 8. And divide that by 246 plus 27. And the answer, my solution, ends up being 0.187. So this also means that I have a very low substrate stability. Again, if you're wondering where I got these numbers from, well, 43 is just my scrapers from down here. 8 is my filterers from down here. I'm just using what the table gave me. So in 2015, this is simply the data that I have. So is our substrate very stable? No, it's actually pretty unstable. It's closer to 0 than it is to 1. So let's go ahead and look at predator control index, and then we'll we'll kind of look forward to Shannon Weiner diversity index, which we'll have in another video. So predator control index, this really kind of gets into the magic of using this, of doing this kind of analysis. So this is what's so cool about this calculation. Predator control index tells us how fast energy is moving through that ecosystem. So you might remember back in first semester we learned about food webs and food chains and ecosystems and things like that. We talked about energy flow, energy flowing. And if energy is flowing through an ecosystem, it means lots of organisms are eating each other. And if it's not, it means there's really not a lot of predation going on. So what's happening here is that we divide predators by everybody else. If there's a lot of predators and we have a high predator control index, then that means that there's lots of energy flowing, and that's really good if you have a lot of energy flow. If you don't, it means that your flow is kind of stagnant and it's not as dynamic or flowing of an ecosystem, if you will. It's just kind of sitting around. There's not a lot of predation going on. So how do we set this up? You just take predators, you just divide it by the sum of everybody else. And this is a pretty simple one to understand because it's almost like a percent, right? It's almost like saying what percent of your organisms are predators. It's not quite, but it's almost like that. So let's go ahead and set this one up too. So when I get this all set up and I take my predators down here, oops, I made a typo. Let me fix that. Okay, so that's fixed. So I take my predators, 11, and divide them by my gatherers, plus filterers, plus shredders, plus scrapers. What I'm going to end up with, 0.034. So this is my predator control index, and that's really quite low. In order to have a predator control index that's high enough for this to be healthy, we would want it between 0.1 and 0.2. And this is actually really, really low. So with that, we are actually done with all of the indexes we'll talk about in this video. There's one more on Shannon Weiner that I want to show you just so you understand how to calculate diversity. But that's basically it for those. I do want to talk to you briefly in this video about what Shannon Weiner is. It's a number that calculates for us how diverse an ecosystem is. And I just want to say one quick word about this, and then you can shut off this video. In Shannon Weiner diversity, we cannot use the feeding groups. We have to actually use individual species. So in the next video, I'll show you how to do that. How do you use individual species to calculate the Shannon Weiner diversity index? But at least in this video, we've covered these 5 indexes, and hopefully now you can understand how do we use these calculations in order to investigate how different environmental changes affect these factors.